All right, hello, and welcome um, to Wednesday lecture. I am just getting my color palette situated, and then we'll be good to go. Hopefully you had a good Tuesday in between our classes. Thank you for everyone for sending all the good vibes my way, and for bearing with a lecture that was missing a webcam. But I'm back. Today is good. It's Wednesday. What's not to like? All right, so we are continuing with our march through chapter 6, and we have, so just to kind of recap, sum up what we've been discussing so far. We have been talking about energy transfer, right? Thermal energy transfer, and we know that that all energy transfer can be summarized in an energy exchange that takes place between a system and its surroundings, right? We've got these two kind of entities, the system that we're focusing on and the surroundings, which is literally the rest of the universe. And in this dichotomy of system versus surroundings, we have two distinct ways that energy can be exchanged back and forth between the two. The first would be energy can be exchanged thermally, right? There's changes in thermal energy, for which we have the expression Q, which is the change in thermal energy is equal to the mass times the specific heat capacity times the change in temperature, all right? And then the second way that energy can be exchanged in between a system and its surroundings is through work. And we know that work is equal to -1 times the constant pressure of the environment times the change in volume. And we spent a lot of time yesterday talking about how in a chemical context, work is done through the expansion or compression of a gas. That's how energy is exchanged through work. And we went all into that yesterday. So at this moment in time, we can truly understand the equation that we wrote at the beginning of this chapter, which is the change in energy. Any change in energy is going to be the sum of the change in energy, the change in thermal energy, plus the sum of the change in thermal. Okay, let's try that again. The change in energy is going to equal the sum of the change in thermal energy plus the change in energy accomplished through work. All right, and that gives us this this kind of expression. Now, when we look at change in energy, delta E, for a specific reaction, so the change in energy that accompanies a reaction. Reactions, just like any process, can be exothermic or endothermic, right? They can release heat, they can absorb heat, depending upon the specific reaction in question. And the change in energy for a reaction, if a reaction is the system that we're interrogating, that we're looking at, just like anything, is equal to the change in thermal energy for the reaction plus the energy exchange through work done by the reaction. Now, something that's worth noting here is in chemistry, most reactions take place at constant volume. All right, most reactions take place at constant volume. All right, that means if volume is constant, that means initial volume is equal to final volume. Therefore, change in volume, delta V, which is V2 minus V1, is 0. All right? And that's true for most reactions. All of the reactions that I did in grad school took place at constant volume. This would be different is if you were a chemist studying gas phase reactions. That may not necessarily take place at constant volume, but almost all chemistry takes place in the solution phase, right? So dissolved in some sort of solvent, and those volumes don't really change. As a result, change in volume is 0. And if you look at what this does to the equation for work is equal to -1 times pressure times change in volume. If this quantity is 0, then that means no energy is exchanged through work. So under constant volume, then the expression for the change in energy for a reaction simplifies to the change in energy for a reaction is just equal to the change in thermal energy. All right, so for almost all the reactions we do as chemists, this is the case. The change in thermal energy will equal the total change for the reaction with all the appropriate caveats that we just mentioned. All right, now, with that in mind, that means that if you can measure the change in energy for a reaction, then, or the change in thermal energy, then you also know the total change in energy for that reaction, and that leads us to a type of experiment known as bomb calorimetry. Which sounds explosive, but it really it's not. The bomb is the name of the apparatus used to take these measurements, and it doesn't explode, or the apparatus doesn't, or shouldn't at least. Hopefully it doesn't explode. But here's the basic idea and setup for a bomb calorimetry experiment. The goal of doing this in the first place, the goal is to measure the thermal change in energy for a specific reaction, so that you know what the energy change, whether this reaction is exothermic or endothermic. Does it release heat? Does it absorb heat? And it uses an apparatus called a bomb, and I've mentioned that already, and this is kind of the anatomy of a bomb in bomb calorimetry. You have right here on the inside a reaction vessel. So you set up your reaction to take place inside this reaction vessel, and in the bomb calorimeter, it's usually an insulated, very kind of thick. The ones that I've used in the past have been like Teflon, and the reaction vessel itself often is jacketed in water. All right, so this thing is filled with H2O. That's there to kind of absorb. Absorb all the heat released by the reaction. released or absorbed, I guess, because reactions can be either. No, that's not very clear. Let's do it in black. All right, so it's the reaction vessels jacketed in H2O, and again, the design of this is to not let any heat escape. Inside the bomb calorimeter, there is a thermometer, and this is here to obviously measure the change in temperature. Right, so you've got your initial temperature of the thermometer that we measure, and then you've got whatever temperature it rises to. Right, where you start and where you finish. Whoops. Let's adjust that opacity. There we go. T1 and T2. Now, with bomb, so we're used to using Q and the specific heat capacity, right? Where Q is equal to mass times specific heat capacity times change in temperature. In bomb calorimetry, we actually use for bomb calorimeters, we don't use specific heat capacity, we use heat capacity. Calorimeters, when they're manufactured, have the heat capacity measured, so chemists don't have to weigh them. So the Q for the reaction, how we measure Q of the reaction is it will equal -1 times Q for the bomb. All right, or let me put Q bomb right here. Because again, just by way of reminder, the reaction is the system, and in this case, the bomb is the surroundings. All right. The change in thermal energy for the bomb is equal to the heat capacity of the bomb times the change in temperature. And so the nice thing about bomb calorimeters is because they don't have a specific heat capacity, we don't have to weigh them, we don't have to incorporate their mass, we're just given the heat capacity for that bomb. We use the heat capacity and the change in temperature to measure the change in thermal energy for the bomb, and then we know that whether the bomb gains or loses energy, that energy came from or went into the system, which is the reaction. So you multiply by -1, and that gives you your change in energy for your reaction. All right, now let's do an example using these concepts. You'll see that they're not nearly as gnarly as the work problem that we ended the lecture with last time. So this will be a bit of a refreshing turn. So, for example, 1.010 grams of sucrose is burned in a bomb calorimeter the heat capacity for this specific bomb is 4.90 kilojoules per degree C. Period. Part A, the initial temperature of the bomb was 24.92 degrees Celsius, and the final temperature is 28.33 degrees C. Determine the change in energy for this reaction. So that's part A, actually. There's also a part B. Part B reads like this: the molecular weight of sucrose is 342.30 AMU. Determine the ratio of change in energy to moles of limiting reactants for this reaction. And then one little piece of information that technically we need to solve it, but so that's why I'm giving it to you. Note, sucrose is the LR. Sucrose is the limiting reactant. Okay. So let's go ahead and give this problem a try. All right. So looking at the first part of the problem, we're asked to find the change in energy for the reaction. Right, we need to find delta E for the reaction, and we know that delta E for the reaction is going to be equal to the change in thermal energy for the reaction, right? When you look at what we're given, we are given the heat capacity for a bomb calorimeter right? 4.90 kilojoules per mole. We're given both a final and initial temperature. Let's see, initial temperature was 24.92. Degrees Celsius. And we know we've got another equation up our sleeve that the Q of our reaction, change in thermal energy for the reaction, is going to be same value, opposite sign as the change in thermal energy for our bomb. And the change in thermal energy for our bomb calorimeter is C times delta T, right? So this is going to be equal to 4.90. Oh, sorry, I wrote this as kilojoules per mole. It's not, it is kilojoules per degree Celsius. Times final minus initial, 28.33 degrees Celsius minus 24.92 degrees C. All right, now we take the difference, right? We got 28.33 minus 24.92. So that difference is 3.41. Still have kilojoules per degree Celsius times the difference, as I just said, was 3.41 degrees Celsius. When you look at the sig figs for this problem, the two numbers we subtracted have their last significant digit in the hundredths place, as does our answer, so we don't need to round or anything. We multiply 3.41 times 4.90, and our answer, well, my calculator's telling me is 16.709. One thing you'll notice is degrees Celsius cancels, and we can only have 3 sig figs. Both of our numbers only have 3. So the energy, change in energy for the bomb calorimeter is a positive 16.7 kilojoules, which means that the Q for our reaction is negative 16.7, and that also means that the change in energy for our reaction is negative 16.7. And that is the answer for part A. All right, that is the answer for part A. Now, we have a second part of this problem that we need to carry out. We're going to use this part moving forward, but let's go ahead and shift gears and look at part B of this problem. So we're told that the molecular weight of sucrose is 342.3 AMU, and we're asked to determine the ratio of the change in energy to the moles of limiting reactant. So we're told what we're trying to find right there at the end of the problem. We're trying to find the ratio of the change in energy for the reaction to the moles of limiting reactants. All right, and you'll notice we're given the grams of limiting reactant, 1.010 grams of limiting reactant. We're given the molecular weight is 342.30 AMU of the limiting reactant sucrose. So we know those two. The problem does not explicitly state the change in energy for the reaction, but we actually solve for this in part A. So if you're working a problem and you're like, it seems like there's a missing piece of information. It could be that you actually found that missing piece of information in a previous step. So always keep that in mind as you go about your business. Now, to find the moles of limiting reactant, we need to employ our molecular mass, right? We need to put grams of our limiting reactant in the denominator, moles of limiting reactant in the numerator, and we're given our molecular weight. There's 342.30 grams of limiting reactant in 1 mole. Right, so grams of limiting reactant cancel. And we go 1.010 divided by 342.3. All right, and this equals 0.00295063. All right, moles. When you look at your sig figs, we can keep 4 of them. 1, 2, 3, 4. I'm going to wait around to the very end, but I'm putting these lines here to remind myself that we have 4 significant figures. So now our ratio for the change in energy to moles of limiting reactant, we put our moles in the denominator. Oops, there's 4 sig figs in the denominator. And then our energy units in the numerator, we've got 16.7 kilojoules. All right. And now we divide one by the other. All right, so this comes out to be let's see, 3 sig figs, 5,660 kilojoules per mole. All right, that is the answer for part B. Oh, sorry, I just saw Caitlin's question. And that is a negative 16.7 kilojoules, and so my answer should be negative 5,660 kilojoules per mole. Okay, Kate. Great question. And the answer is not necessarily. Here, hang on 1 second. So, Kate, the answer to your question is when change in energy is negative, it's an exothermic reaction. That's true. That means that the system is releasing energy into the surroundings. But the thing to remember is this. Your total change in energy is the sum of thermal energy transfer plus energy transferred through work. So you can have a exothermic reaction where no work is done either by system or surroundings. So you can also have an exothermic process where no thermal energy is exchanged. Yes, totally. So exothermic means energy is being released, but it's important to remember that there are two different ways energy can be transferred. And just because energy is being released doesn't mean that work or thermal energy is involved. Both could be involved at the same time, or just one could be involved. It changes from context to context. Excellent question, though. Great observation. Okay, so let's see where we are. Okay, right. So that's bomb calorimetry. It's a specific type of experiment used to measure the change in energy for a reaction. And that brings us up to a quantity that is super important, and it is known as the change in enthalpy. All right, change in enthalpy. Change in enthalpy is symbolized with a delta H. All right, symbolized with a delta H. That is change in enthalpy. Now this is, I feel like entropy gets a lot more coverage kind of in popular conversations, discourse, dialogue, etc. But enthalpy is arguably, it's often they're talked about together, enthalpy and entropy, because they're both thermodynamic quantities. Of the two, enthalpy tends to be the more powerful, but it's not as kind of doesn't grab the imagination as like entropy, chaos, all this stuff. We like to talk and think about that stuff a lot more than enthalpy. So it's funny because it's not as popular. You don't hear that word being thrown around like you do entropy, but it has more of a factor in controlling thermodynamic situations. And you'll get into the relationship between enthalpy and entropy more in 401, second semester Gen Chem. But for now, we're just talking about enthalpy. All right, now enthalpy is, like, simply put, your change in enthalpy delta H, change in enthalpy for a reaction, is equal to the change in energy for that reaction. It's a ratio. The change in change in energy for that reaction over the moles of limiting reactant. So we actually stealthed it into the last problem here. It's a ratio, and it is far and away more useful to talk about the change in enthalpy for a reaction than the change in energy. And here's why. The change in energy for a reaction depends upon the quantity of reactants used. So if you were to calculate the change in energy for a reaction where you burned 1 gram of wood, that would be a different energy change than if you burned 1 kilogram, right? 1,000 grams of the same sample of wood of the same tree. The larger sample will release more energy because there's more of it, right? Enthalpy, though, is a ratio. It's a ratio of energy to moles. So it's the same no matter what. The combustion of hydrogen has the same delta H no matter if you're using a lot of hydrogen or a little hydrogen, because it's an energy to moles of limiting reactant ratio. All right. It's very, very useful, very powerful. Some things that we'll already know from our discussions of gaining and losing energy. If your delta H is negative, this means that your reaction is exothermic. Oh. That means you've got an exothermic reaction. All right, when your change in enthalpy is positive, that means you've gained energy, and this is an endothermic reaction. All right, just as we've already seen, positive means we've absorbed, negative means we've lost, endo and exo. Now, here is where delta H, change in enthalpy, really shines. All right, and actually, let me move this over just a tad. When you are dealing with an exothermic reaction, right, a negative delta H, this means that energy is released, right? In other words, you can treat energy as a product of the reaction. All right, it's released, it's produced by the reaction. When delta H is positive, when you're endothermic, that means that energy is absorbed. In other words, energy is a reactant. You can treat energy as a reactant for your process. All right, and when I say you can treat it as a reactant or a product, I mean that you can literally write it into your balanced chemical equation. All right. Here's what I mean. If you have an exothermic reaction, and I'm just going to say, let's say you have a reaction where A reacts with B to produce C. If this reaction is exothermic, that means that energy is released, and you can literally write in the value for your change in enthalpy on the product side of the equation, because in addition to producing C, it's also releasing so much energy, right? The value for delta H. When you are dealing with an endothermic reaction, let's say you have a reaction where D is decomposing into E and F. For an endothermic reaction, you can write in your value for delta H on the reactant side, because in addition to consuming D, the reactant, it's also absorbing, essentially consuming so much energy, and that value for energy is given to you by your delta H. With this knowledge, we can do examples like the following. All right. So consider the following. Example. Carbon tetrahydride reacts with oxygen to produce carbon dioxide and water. Right? The delta H for this reaction is negative 802.3 kilojoules per mole. All right, part A. Write a balanced chemical equation for this reaction. Part B. Let's see. Part B is Angelina, great question. This totally is a combustion reaction. If 57 kilojoules are released, comma, how many grams of CH4 combusted? All right, now let's take this one step at a time. One step at a time. First, let's write a balanced chemical equation for this reaction. So we're given that we have carbon tetrahydride, so that's CH4, reacting with oxygen, which we know is a homonuclear diatomic, O2, producing CO2. Oops. Oh, goodness. Okay, hang on. There, finally legible too. Plus H2O. All right, and now we have to balance this chemical equation. So we have carbon, carbon, hydrogen, and oxygen. On both sides of this reaction. On the reactant side, we have 1 carbon, 4 hydrogen, and 2 oxygen. On the product side, we have 1 carbon, 2 hydrogen, and then 2 oxygen from CO2, 1 oxygen from H2O. All right. I always say focus on the simplest ratios first, save the hard stuff for later. Hydrogen looks pretty straightforward, right? 2 goes into 4 2 times, so we need to multiply H2O by 2. And when we do, we balance hydrogen and change our oxygen count. So we have 4 hydrogen, and now we have 2 plus 2 oxygen on our product side. But now that that's balanced, we've actually made it a lot easier to balance our O2 because we have 4 on the product side, 2 on the reactant side. So we need to multiply O2 by 2, and that will balance our chemical equation. All right. So that is part A. Let's take a look at part B. All right, let's take a look at part B. So we are asked to find or I guess to FID if my canvas is to be believed right now. So we're asked to find the grams of methane that react, right? And what we're given one of the things we're given is our balanced chemical equation. We're given 2 things. We're told that 57 kilojoules are released, and we're told that the delta H for this reaction is negative 802.3 kilojoules per mole. Now, this might seem difficult. This may seem like I have no idea how to move forward, how to tackle this problem, and it will feel that way until you remember what we were just discussing about delta H. Delta H actually belongs in your balanced chemical equation as either a reactant or a product. All right, so the fact that it is negative tells you that this belongs on the product side. And so to solve this, you should write in the value for your delta H on the product side of the reaction. So 802.3 kilojoules. Just kilojoules. You're going to drop the per mole when you write it into the reaction. We'll talk about why in a second. But you'll also notice that I don't write negative 802 kilojoules, 802.3 kilojoules. I just write a positive. Some students find this confusing, but remember, and this is clutch, the sign of delta H. Sign of delta H, which is positive or negative, all that tells you, it just tells you reactant or product. It just tells you what side of the reaction to put it on, but once it's in there, you write it in as a positive. There's no such thing as negative energy, right? At least in a physical science perspective. There's people dragging you down with their negative energy. That's a thing. But when it comes to thermodynamics, there is no such thing as negative energy. A negative sign for energy just tells you the direction it's flowing. So a negative delta H just tells you that this is being released. It's energy that's being released, right? So whenever you write it into your chemical equation, do so with a positive sign. Now, here's how you use this information. And actually, I wrote my energy in the wrong layer, so let me rewrite it here. Plus 802.3 kilojoules. All right, you may be wondering, but what about the per mole? That comes in when you use this in the context of this reaction, all right? So we were told that 57 kilojoules of energy was released, and we're asked to find how many grams of CH4 reacted. what we need is some sort of unit conversion, some sort of ratio that could take us from kilojoules to moles of CH4. And you know what's cool is this balanced chemical equation tells us that for every 802.3 kilojoules of energy produced, 1 mole of CH4 reacted. So we put a 1 there for moles of CH4. We put 802.3 kilojoules in for energy. Kilojoules cancels kilojoules. The next step, we need to convert moles of CH4 to grams. All right, and that unit conversion, that ratio is 1 mole of CH4 is 16.042 grams of methane. Okay, Kyle. Kyle, great question. Kyle, so you're going to put the 802.3 kilojoules in the equation because you always put the value for delta H. So if you look back at the original problem, which is right here, I give you delta H. Whoops, nope. Let's go right here. I give you that delta H is equal to 802.3 kilojoules per mole. So that's what goes in the reaction. The 57 joules that are released, that's what we're using for the calculation. Yes, Angelina, you totally can, and we'll actually do that in 1 second. I'll highlight how that goes down in just a minute. Nope. Well, and in this one, actually, Angelina, we haven't been told which one is the limiting reactant. But we can use the value for delta H to relate to any reactant or product in this reaction. I'll show you oxygen in just a minute. First, let's just crunch these numbers. 57 divided by 802.3 times 16.042. This comes out to be, oops, no, sir. There we go. This comes out to be 1.1397, but we can only keep 2 sig figs, 3 rounds down. So this will come out to be 1.1 grams of methane. React to produce 57 kilojoules of energy. Amanda, that 16.042 is the molecular weight for CH4. which is found by adding the mass of one carbon atom plus the mass of 4 hydrogen atoms. And that is the number of grams in 1 mole of CH4. So that's where that comes from. All right. Now, you can use delta H to relate an energy quantity to any reactant or product in your chemical equation. So, for example, I didn't ask this in the problem, but if I had asked you to find the grams of oxygen that would react, Amanda, you are so totally welcome. We would need a conversion factor to convert from kilojoules of energy to moles of O2. And the balanced chemical equation shows us that 802.3 kilojoules of energy are produced when 2 moles of O2 react. All right, so you can use this quantity or use delta H to relate to any quantity in the balanced chemical equation, and you do it just like you do any mole-to-mole ratio, right? You just look at what the number is in the balanced chemical equation. That's what you use for your ratio. To get grams of oxygen, we got to convert from moles of O2 to grams of O2, and I'm not gonna write this out. The mass of oxygen is 16.00 AMU, and so 2 of them will be 32.00 grams per mole. And moles of O2 cancel. And now we can crunch these numbers. We've got 57 times 2 divided by 802.3 times 32.00. The value that I'm getting is 4.5469. But again, we get around to 2 sig figs. 4 will round down. And so our final answer is 4.5 grams of oxygen. All right, you can, and this is truly the power of delta H. It allows you to relate energy quantities to any other quantity of any other reactant or product in your balanced chemical equation. So all the stoichiometry stuff that we know how to do with masses, with molarities and volumes, now in light of chapter 5 with pressure, volume, and temperature relates to stoichiometry if you're dealing with a gas. Now energy relates to stoichiometry. So all those things that we learned, limiting reactant problems, excess reactants, theoretical yields, percent yields, we can do all that with energy in the mix. With energy in the mix as well. Okay. Now, we're about to journey into a section of, we're still talking about change in enthalpy. And we're going to move towards something known as Hess's law. All right. But before we get there, I want to kind of lay down the relationship between change in enthalpy and chemical equations, and how when one changes, how it affects the other. All right. Now I'm going to write out these rules, and they might seem a little abstract. You might not understand why I'm doing this or how they're going to relate. I just want you to hang with me. All right. I'm going to write them out. Just find these relationships, and then you'll see how we apply this when we talk about Hess's law, which will probably be on Monday. So hang with me for these. If you don't know why you need them, you will probably on Monday. Definitely on Monday. Depends upon how far we get today. So first, I want you to consider a chemical reaction. I'm going to call this reaction 1. And in reaction 1, you have 1 mole of compound A reacting with 2 moles of compound B to produce 3 moles of compound C. All right. And let's say that reaction 1 has a change in enthalpy that is, we're going to call it delta H1. All right. Now consider reaction 2. All right, reaction 2. Reaction 2, let's say, has 2 moles of A reacting with 4 moles of B to produce 6 moles of C. Now, I can already hear the protest in some minds saying, like, wait a minute, that's not the simplest whole number ratio. Balanced chemical equations only have the simplest whole number ratio. It's true, but just roll with me. You're going to need to use this in a future problem. So just suspend disbelief for a little bit. The delta H for reaction 2, the second reaction, you can notice that relationship between 1 and 2 is reaction 2 is the same reaction, just with everything multiplied by 2. The delta H for reaction 2 is equal to 2 times the delta H for reaction 1. All right, so if you multiply every reactant and product in a chemical reaction by a number, the way delta H changes is you also multiply delta H by that number. Oh, I just called this reaction green, I'm realizing now. Let's fix this up. All right, so that is the first relationship. Let's talk about another relationship. Let's look at, we're going to call this reaction 1 again. And let's say reaction 1 is has 1 mole of A reacting with 2 moles of B, also to produce 3 moles of C. I'm actually going to use different colors this time around. Still calling this reaction 1. And the delta H, we're going to call delta H1. Now looking at reaction 2. Reaction 2, in reaction 2, you have 3 moles of C decomposing into 1 mole of product A, product A, plus 2 moles of B. We're going to call the delta H for the second reaction delta H2. All right. Now you'll notice that there's a relationship again between 1 and 2. Delta H2 is just reaction 2 is just reaction 1 flipped, right? The product for reaction 1 is the reactant for reaction 2. The reactants for reaction 1 are the products for reaction 2. And the change in enthalpy for reaction 2, if you flip a reaction, is equal to the delta H for that first reaction times -1. So if you flip a reaction around, the new delta H for the new reaction is just the same quantity, opposite sign. All right? Now, those are 2 of the relationships that I wanted to discuss. There is a third and final. So consider a reaction, which again I'm going to call reaction 1, where you have 1 mole of A reacting with 2 moles of B to produce 3 moles of C. And a second reaction, which I will call reaction 2. In which 3 moles of C produce 3 moles of D. Sorry, I forgot. I'm realizing to state my delta H's. I'm going to call this delta H1. And this second reaction will have a delta H that's delta H2. All right, now, if you add these two reactions together, you add 1 plus 2 to get a new reaction, which I'm going to call reaction 3. All right, this is something new. If you add reaction 1 plus 2, you'll notice that 3 moles of C are on the product side of one and on the reactant side of another. So they will cancel, as we've seen already, right, with balancing redox reactions, with net ionic equations. If you've got something on the reactants and the product side, they cancel out. So reaction 3, we get reaction 3 from adding reactions 1 and 2 together, and our reactants for reaction 3 are A reacting with 2B to produce 3D. All right, and this will have a new delta H, which we're going to call delta H3. And the value for delta H3, the delta H of this third reaction, will be equal to the sum of the delta H's for the reactions that you added together to derive the third reaction. All right? So that is the third relationship. If you add a couple reactions together, the delta H for that new reaction will be the sum of the delta H's for those reactions that you added up. All right? Now, all right, this brings us to the precipice of a new example. And I'm looking at the clock. We've got like 9 minutes. And so here's what I want to do. I don't want to rush this problem because I want to kind of give it room to breathe, take time. I don't want to be like slam into the very end to try to finish it in time. So what I'm going to do is I'm going to write this up on the board, and I'm not going to do it now. So cliffhanger. You'll have to tune in on Monday to see the resolution of this example problem, but give this a shot over the weekend. Angelina, great question, which I'll answer in just 1 second. Try this over the weekend, see if you can do it. Then come to lecture, watch me work it, see if you got the answer correct. If you don't, you can learn something, see where the mistake was, what tripped you up. Or if you cannot possibly wait till Monday, you can always drop by an office hours tonight and ask me about it. Angelina, that is a great question. These relationships are only true for delta H. Not change in energy, just change in enthalpy. All right. So here is, try this example on for size. And I'll say a little bit about how to approach this, so that you have something to go on. Take a shot at it, and we'll come back and solve it on Monday. Wednesday, if you ask me about it in office hours, I guess. So determine the change in enthalpy for the reaction where solid carbon reacts with water vapor to produce carbon dioxide gas and hydrogen gas. All right, now here's what you have to go on. So we want to determine the delta H for this reaction, given the following thermodynamic information. The combustion of solid carbon, so the reaction of carbon with O2, gas to produce CO2. Gas has a delta H of negative 393.5 kilojoules per mole. The reaction of carbon monoxide with oxygen to produce carbon dioxide. So this is, I guess, the combustion of carbon monoxide, as weird as that is to think about. This reaction has a delta H of negative 566.0 kilojoules per mole. That's not a typo on the first reaction. CO2 is the product, but you can see that carbon monoxide is a reactant in the second reaction. And then finally, it's going to be a third reaction you have to go on, also combustion. H2 gas plus O2 gas produces H2O. And the delta H for this reaction is negative 483.6 kilojoules per mole. All right, now that's a lot of information. You may be unsure of where to start, and I can tell you that it will take more than the 3 minutes of lecture, remaining 3 minutes of lecture to solve this problem. So I'm going to give you kind of like a guiding light, a strategy. All right, so here is how you want to approach this problem. You want to manipulate the given reactions so that everything everything that is not in our goal cancels. All right, so you want to take the relationships that I spent the close of lecture kind of developing. Like you multiply a number by, or a reaction by this number. This is how the delta H changes. Manipulate these three given reactions so that everything that isn't in that goal reaction that I boxed in green will cancel out, and then add them all at the end so they cancel, add all the delta H's, manipulated delta H's, and that will be the delta H for this reaction. If you want to see me do this live tonight, I'm more than happy to do it for you. If not, totally no problem. Give it a try over the weekend. We'll come back on Monday and give it a shot. So that's where we're gonna call it. Thanks everyone for showing up, and your kind words over the past couple days have been really, really awesome and meant a lot. I'll see some of you in office hours tonight, and the rest Monday after the weekend. Later, dude.